Chapter 4, 50 Shades of Slate. Deciphering rock colors. This is actually going to be chewier than you think. So you have your cleaned and prepared specimen, and we're ready to tell what color is it. And you might be going, it's a rock, it's gray, whatever. But there's hues, and there's noticing where the color is, and if there's multiple colors that are really important. In fact, we're going to be inspecting our specimen for different colored areas to see if it's a rock or a mineral, because oftentimes a rock will have different colored areas where the different minerals are. However, a mineral oftentimes will be a solid color, but not always. So no matter if it's a rock or a mineral, we are going to note all the colors in different states. But first we have to get really good light. So if you are not blessed with sunlight often, full spectrum lighting will do. However, just know that rocks will shift in how they appear visually to you in different colored lights. My ring light and my aught light and my incandescent but full spectrum replacement LED light and my fluorescent light are all going to show slightly different color hues, and that is something you might want to note. Many stones are actually different colors in different lighting, and that's important. So this is a time where we're going to take a lot of notes. Is the rock dark? Is it light? Does it have different colored spots? We kind of touched on this earlier. Is it a mineral that when you hold it one direction it's one color, but you change its direction it's another color? We want to examine it from all angles dry. So if we're looking at this specimen, we would see that it has a reddish ochre orange outside that's rough. We would have maybe removed this with iron out, or this is just the natural way I found this rock. And then I actually chose to cut into this rock. So this is a cut surface, and it appears just kind of gray with all the scratches in it. So I would document that on my handy dandy worksheet. In your ebook, which in earlier we went over preparation and cleaning a specimen, all that stuff. So I prepared this specimen by grinding an edge, and we're going to go ahead and take a look at what it looks like wet, because this is very important. It can change the look of a mineral or rock a lot. Whoa, what a huge difference. Now I see hues of a grayish purple, green, beige, tan, all kinds of beautiful colors that before I just saw gray. Let's do another. Oh, here's just a little one. So here's where I've ground it to open up the inside. We can see there's a pattern, but we can't really tell until we wet it down. And once again, it's got that ochre red color on the outside from iron staining. This is actually a jasper nodule. It formed like this with the flat top, and whoa, look at all those colors on the inside. So as you can see, you definitely need to do a dry examination and a wet examination, because things change so much. Hi, my name is Laura Jokey, and I wrote a book. It's about rock and mineral identification, and you can find it in my website. There's a link in the bio, or rockyourworldgems.com. Weathered surfaces, what are they? So that's the outside surface of a rock and how it looks after nature has happened to it. This is a great example. I found it on the beach, and this here is the weathered surface. As you can see, there are little fingernail-like marks. That's how cryptocrystalline quartz weathers. Those are its fractures. We'll get into that in another chapter. But this is how it weathers. There's a little bit of white splotchiness. There's some brown to it. And then I noticed what actually made me pick it up was this fracture. So this is not weathered. This is what's called a fresh fracture. And I can see the conchoidal fracture on it, but that's for another chapter. But what this is an unweathered surface. So we're going to document the color of the weathered surface, which is a brownish tan color that fades in and out. And then we're going to document this weird green-brown color of this broken surface. And we're also going to document, let's see if we can catch it, the sparkles, which I didn't actually I kind of caught them, but it wasn't until I polished the surface. So sometimes you have to really prepare a surface, not just wet it, but polish it in order to see that there's little sparkles. This one has either marcasite or pyrite sparkles in it. This is more things to document on your handy dandy worksheet. So, weathered surface is the surface that nature has been very mean to. Fresh broken surface is what we also want to inspect to see closer to what the guts are. And then you have your prepared surface, like our sawed surfaces from the last water test, or a polished surface. Now, a polished surface can take the place of a wet surface because you're essentially doing the same thing. You're filling in the molecular gaps so we can see all the little details. So here's another thing we're going to do. So we're going to hold up a light to our rock. Most people would not think that a light would shine through this rock. However, I am going to attempt to shine this light through this. We have this fresh broken surface and this polished surface. So this thin area, oh, look at that. It's translucent. Now, there is a translucency test we will be doing, but we want to note the color. What color is it when we shine our light through it? Note and document on your worksheet the color of the weathered surface, the color of the freshly broken surface, the color of any wet or polished surface, and the color of a backlit and illuminated surface. You want to document every color. If you have a UV light, shine that on your specimen in a dark room. If you have a long wave and short wave UV light, even better, more evidence, because we are gathering evidence. That's the whole point. Ooh, it's kind of spooky here in the dark. I shall use my rock and UV light to light my way. Look at that, another clue. Mauve and green. Whoa! Wow! Wow! Not everything's going to be as awesome as that ruby, but so I can see on this apatite, which is very hard for you to see on the camera, that it fluoresces slightly pink, so that's something I would document. Oh, and sometimes only part of a stone will fluoresce, so check this one out. Oh, you can't really see, but it actually has like yellow lines in it, so that's something I would document. There's certain places where there's yellow lines and other places where it does nothing. Okay, so I guess that part of color was simple. If you have made it this far, you get a cookie. So remember to buy yourself one at the grocery store next time you go. You're going to make sure to prepare your surfaces, prepare your specimen. You're going to observe it to see if it has one color, multicolors, colors in different directions. You're going to document. You're going to observe it dry. You're going to observe it wet. You're going to observe it in the sun, just for fun, in the rain, on a train, in a boat, on a plane, in your sleep. Take a peep. Whoa, I'm starting to get a flow. Anyways, so you've observed the color of the rock. You've also taken every resource you have, every different color light, and you've shown it on the rock, and you've documented your face off. Why does the rock change color in different lights? Stay tuned to find out. So color is the different waves that make up white light broken apart and either reflected back to us or absorbed by an object. So that is what color is. From red to violet, Roy G. Biv, the rainbow. For more information on color, there's some amazing articles online about like the deep dive into like what exactly color is. But essentially color is energy. It is a wavelength, and being energy, it affects electrons in atoms. And so that is one way, well, that affects rocks and minerals and other things in a multitude of ways that light impacts things. We're going to talk about all the different ways that color is produced. So the headiest, most complicated way we're going to get out of the way first, and that is that when a rock or a mineral has certain metals or particulates within the atomic structure, what can happen is the light's energy can actually change the position of an electron and change what color. Instead of white light, it bounces back, say, blue light or red light, because that electron moved. That's what's a color center. You can also get it where some metals and other elements will replace a part of an atom. And so the blue that is in amazonite is actually from a lead ion hanging out in the feldspar. When we have these changes in atomic structure, it changes how white light, which is all the light, comes and reflects back to our eye. Amethyst is colored this way. So the iron that colors the amethyst, the Fe3, actually has shifted where its electron sits, and that's why it's purple. If we were to heat it, it would move that electron back, and it would turn into citrine or clear quartz. So radiation can also cause electron disturbances. So that's where you get like the black and smoky quartz, is that radiation has disturbed the aluminum within the smoky quartz, and it's now giving you back the black. So these things that cause disturbances in the light wavelength on an atomic level within the stone are usually in the transition metal element family, but they're not always. But those are copper, nickel, iron, cobalt, manganese, chromium, vanadium, some rare earth elements, uranium, and in the case of smoky quartz, aluminum. So it's not always this list, but these are the most likely culprits. And it's essentially when those are within the atomic structure of the rock or mineral, and their electron has been forced to shift, it throws back a different color to you than white light. These are color center minerals. For instance, that ruby that glowed hot pink in the UV light, that's because of chromium within the aluminum oxide structure that's absorbing the blue and kicking back the red. Hi, my name is Laura Jokey, and I wrote a book. It's about rock and mineral identification, and you can find it in my website. There's a link in the bio or rockyourworldgems.com. So physical structure can also determine the color of a rock or a mineral. Crystal structure itself might allow or disallow light to pass through it or refract based on the structure of the crystal. There's iridescence from thin films of mineral that reflect back a rainbow or oil slick-like color. There's diffraction, which are spaced layers that act like a prism, like in labradorite or opal. Opal being a mineraloid of little spheres of silica in a water base, and labradorite being different layers of plagioclase and a little bit of the orthoclase feldspar being layered and giving that prismatic effect as well. So that's called diffraction. We also know that the physical structures of certain chalcedonies can affect the color, like Ellensburg blue. Right now they're still trying to determine what exactly the trace minerals and elements are in the Ellensburg blue agate, and if you have that answer, please put it in the comments. However, last I heard, they're just still trying to get a large enough basis for that. But anyways, with the Ellensburg blue agate, the color is blue like the sky for the same reason the sky is blue. It's the structure of the chalcedony refracting everything but the blue back to you, only the blue. And when you hold it up to a light though, it's got a pink background. So those are some of the mysteries that we're still trying to solve, and we're pretty sure it's from physical structure, but we're still not sure if there are metal transitional ions that are affecting Ellensburg blue agate. So that's something that science has yet to figure out, but we're working on it. Now, the other way that minerals get colored is that there's literally so much of another mineral or element in it that that color of that takes over it. So with the Oregon sunstone, you have a lot of copper within the stone, making it have a copper silver color. With the Tanzanian sunstone, you have hematite making the orange color. There's blue quartz from Virginia that has ilmenite and rutile that causes the color. So sometimes the color in a rock is that color because it's got a bunch of other minerals in it. So you got to figure out what minerals are in the crystal or the rock structure in order to figure out why it is the color that it is, or what in fact it is. So with over 5,000 mineral species, scientists have supposed up to about 13 different ways that they essentially produce color to human vision. However, science is still out on some, and some we're pretty sure about. The biggest thing to understand is that how color works, and that light impacts color, and that this is why we go through such an extensive testing process to make sure that we have observed as much of the different colors of this rock that it can produce to a human eye. So there you have it, all the shades of color. On to luster next. See you there. Hi, my name is Laura Jokey, and I wrote a book. It's about rock and mineral identification, and you can find it on my website. There's a link in the bio or rockyourworldgems.com.